I didn't get my sound. Do I have my sound? Oh, I have my sound off. Oh, I found a new. Oh, I gotta show you. Where is it? Oh yeah, in here. Here, I'll do it in our presentation, just so we have evidence. I found a new use for the magic bar thing on here. 300, right? So it's so exciting. So watch this, watch this. So I'm gonna put, when I do my drawing, and sometimes I just put a straight line like this, and then I decide, oh, I want this to have an arrow on one of the ends, right? I click there, and I click there. I got an arrow on that side, and then I got an arrow on. Oh. Ha! I can put dots
So
down.
does it actually show you the arrow on the?
Yeah, it's like, you know, I got all sorts of choices up there. I can switch it to none. Oh, that's only, oh, none on both. Oh, I get two different controls. What's this guy? Oh, look at that! I get a slider for line thickness, line color. Oh, so good. What's this guy? Oh, look at that. Looks like a chalk line. What if I put arrows on the end of that? Are they chalk? Oh, yeah. Oh.
$800 well spent.
Well, let's see if I can do my emoji in here. It's my favorite. My favorite. Can I do it? Yeah. Oh man. So easily. I'm just leaving that there. Easily entertained. All right. So we got to write reverse real quick, right? For our A list. Let's see, where's, well, I should leave that expanded. I won't be able to find it again. Is this us? All right, so we're going to go into, so our A list is represented as a string array. So we're going to come in here, we're going to write a public method that's not going to return anything because it's just going to reverse the array. And this guy is going to be called reverse. Actually, was it supposed to return a new A list that's the reverse of the original, or was it supposed to reverse the A list in place? Reverse it in place? Okay, yeah. So this guy's going to return void. All right. So we're going to go ahead and create a temporary string array that's the same size as our original one. So we'll say string array temp is equal to a new string array of size this dot data dot length. And then we're going to have our little for loop, and you know, let's start at the end of data. All right, so for int I is equal to 0, I is less than, I'm sorry, I is less than the last legal bucket of data, so this dot data dot length minus 1. I is greater than or equal to 0. I minus minus. All right, and then each time through, we want to copy bucket I from data into bucket whatever of temp. So we don't have a counter for temp. So what we can do is we can give ourselves a counter out here for temp. Maybe we call it pause, and we start pause off at 0. We could also do that counter in here. So I don't think I've shown that to you before. You can have multiple counters inside of a for loop. So I could say int pause is equal to 0, comma, int I is equal to that, and then over here I can say pause plus plus if I wanted to. Okay, so I can do multiple modifications inside of a for loop if that makes me happy. It's screaming right now because I have two things there. Now I don't need to define the second int because these guys are both ints. So the syntax for that is int pause is equal to whatever, comma I is equal to whatever. So this only allows you to define counters of the same type. You don't have to do it this way. In fact, I would say it's somewhat uncommon. There's not a great reason for that, but somewhat uncommon to include that second counter inside the for loop, but you can do it. And remember, it follows the same rules as your original counter is going to follow, and that is when this for loop ends, the scope associated with that for loop also ends, so we will lose I and pause. Not the end of the world in this case, because after this is done, we don't need either of those. But if you happen to need the value of pause after this, yeah, probably wanted to instantiate it outside of, you probably wanted to define it outside of the for loop. That way you had access to it after the for loop. All right, so I is counting down, pause is counting up, so we're going to be putting this guy into this position of temp. All right, so we'll say temp is equal to this dot data at bucket. Temp is equal to temp at bucket pause is equal to this dot data at bucket I. We'll let that guy do his magic. Remind me, did I need to say this dot in front of here? Okay. Why not? Yep, it'll look for the most local definition of data. So if I don't put this dot in here, it's going to look inside this local scope and not find it. Then it's going to jump up to the next most local scope, which in this case would be our global scope, and it'll find it up there. So putting this dot data has two advantages. One is a performance advantage because it's not going to now look locally. It's not going to look in this local place here. I'm telling it to go directly to the top global scope. So that's faster. It also has the command completion stuff. So I can say this dot, it allows, I don't have to misspell my variable and that stuff. So two benefits. I don't know. I think for me, that the second one's the major benefit. I don't think the speed is that huge of a thing, but whatever. All right. And then after I filled up temp with all of the stuff from data, I'll set this dot data equal to temp. So I've actually reassigned this dot data to point to a new place in memory. If for some reason that was a bad idea, I could always copy the contents of temp now over this dot data. Okay, because do understand that what I just did here, let's assume that some other part of my program had access to data. So had another variable that held the same memory address of data. Okay, so both of those guys pointed to the same place. Well, what I just did here is I made data now point to a new place. Those guys are no longer linked. That makes sense? So something to consider. As I've written it here, data is now a new memory address. But for everybody who accesses data after this fact, who uses our A-list, they're using the new memory address. No harm, no foul. But if anybody happened to be using data prior to this and held on to that memory address, they're no longer working with the same memory address. That makes sense? Now, it won't end up being an error for them. That memory address would not have changed. It would not have gone away because our pointer count would not have gone to 0. Just because the address associated with this dot data initially here now has one less pointer counter after we finish this method. That other guy that was pointing to him would still be something that points to that memory address. So it would still persist. It would just be the old version of data, not the new one, and any changes we do here wouldn't affect this. Make some sense? So all pointer stuff. What's this guy complaining about? Oh, I must have given you like the starting point for the reverse method down here. Yeah. All right, so is that reverse? I think that'll probably do it. We have a display, right? Yep, we do. All right, so we added A and B, then we display it. Then let's go LST dot reverse, and then let's display it again. So it should be AB the first time, then BA the second time. AB, then BA. So that's reverse. All right, now we're supposed to write sort, correct? And sort is supposed to be a quicksort. All right, and I think I showed you in class last time the hybrid quicksort, right? That has the insertion sort as part of it. Well, actually, it's kind of a hybrid insertion sort too, but built into it for the kind of the bubble up. All right, so public. Actually, I'm going to make the quicksort a private method, and then we'll have a public method called sort that actually does that whole starting point, starting for high-low, or low-high, or whatever. So we'll have a private void sort, and this guy is going to take in our int low, int high, and then it actually won't need our array because we have the array. We have access to the array up here already. So I just need to know this particular call to sort, which section of my array is he responsible for. That make sense? Okay. So if we go back here, we looked at our algorithm last time. Oh, tennis ball. Shiny, like shiny lights, right? It's like a kitten. All right, so what we do initially is we pick a pivot. And, we talked a little bit last time about some performance implications, if you will, of picking certain pivots. And I think we decided that setting pivot equal to low plus high divided by 2 gave us decent average performance, and always kind of put the pivot somewhere in the middle-ish, depending on whether we're dealing with a even number of buckets or an odd number of buckets. So with quicksort, what ends up happening is we do effectively we move the pivot to its final location first, right? Okay, and then we call sort again on everything before that and everything after that, because those guys aren't done. Okay, but that dude there, we don't need to touch that part of the list again. Okay, that guy's cooked. Okay, so we're going to go ahead and we're going to pick a pivot initially in our sort. Actually, this guy was going to be the Q-sort. And then we're going to have the public method sort. Okay, and sort was going to take no parameters, and he was going to do that initial calculation of high and low, which is easy, right? So all this guy's going to do is he's going to call this dot Q-sort, and he's allowed to call it because it's a private method, but we're inside of the A-list class. And he's going to pass low as 0, and high is going to be this dot data dot length -1. And we maybe want to say if this dot data dot length is greater than 0, then do this crap. Let's not waste our time calling that if we don't have anything to actually, if it's greater than 1, really. Because if it's 1, it's already sorted. Let's not waste our time, right? All right. So what does that mean? This guarantees that high and low are different numbers, correct? Okay, worst case, there'll be 0 and a 1. So that'll save us a little error checking inside of our actual quicksort to make sure that we don't zig when we should be zagging, that kind of thing. All right. So for quicksort, we're going to pick our pivot first. So int pivot. And we decided pivot is low plus high divided by 2. So low plus high, high, is that how I spell it? Divided by 2. Do I get a tennis ball in here? It's upsetting.
There's limitations.
I bet you it works in Xcode. Because Xcode with Swift, you can you can actually name your variables in Swift with emojis. It's like completely useless. It's like stupid stuff, but I want to see something here. Bar tennis. Ah! Well, that sucks. Wait, what's that button? Oh, the extreme disappointment right now. And that's an Apple product, so like it's supposed to be compatible with their stupid thing. Just garbage. Okay, so we pick our pivot, and after we have our pivot, so right now if we pretend these guys are all green again or whatever, here, let's just do that. Were they green? What were they? Blue? I think they were blue. All right, so we picked our pivot. So in this case, the pivot's going to end up being the 6. So this guy right here, and actually these guys are currently out of order, right? So let's move some stuff around. So we'll say 3, 1, 6, 2, 7. 4. Well, we could have duplicates. It doesn't matter. Then we'll do another 3. We'll leave the 9 there at the end. Good enough. All right. So we'll pick our initial pivot, which is going to be this guy right here, right? All right. So we have our pivot, and let's go ahead and so we'll say pivot is at bucket 4. Is that right? So low is 0, high is 8. 8 plus 0 is 8, divided by 2 is 4, so this is our pivot. So bucket 4, which happens to be a 7. All right, good. So that's our pivot. So now we actually do the job of trying to position that value in its correct final place. Okay, but as part of that process, we need to make sure everything to the left of that is smaller than that, and everything to the right of that is greater than that. Now, the reality is with Quicksort, we can accomplish that all sorts of different ways, right? Now, you're going to have some ways that are more efficient than others and some ways that are less efficient than others, but this is likely the step of the process that at the end of the day isn't going to make a humongous difference in performance on, let's call it, average size sets of data. Okay, so the hybrid approach I showed you, that insertion sort, what the kind of the purpose of that guy is to give you what's considered decent performance as data sets get larger. All right, that's kind of the job of that hybrid approach, because if you just take kind of a random approach at this, which I think if you look at the official Quicksort algorithm. It effectively goes from low to high, and I mean it's essentially a sequential type of move, right? And it does some swapping along the way. There's nothing really special about it. It takes some, just kind of goes about it. There's a little optimization in there. I think there's an interesting if statement, if I remember correctly, and how it does it. But regardless. It's not like this amazing algorithm for moving these things around, right? So ultimately, our goal is to get all the stuff in this list that's smaller than this dude to the left of him, and all the stuff that's larger than this dude to the right of him. But we have kind of one constraint. That constraint is we got this many buckets. Okay, so I mean, we certainly could just create a new array and have lots of wiggle room, right? And move stuff around. But the reality is we need to be shifting stuff around, because as some of these things move to the left of this guy's going to have to kind of go this way and things like that. So we're kind of working in kind of a confined space. So any algorithm we use for this reordering needs to kind of take that into consideration. All right, so what we decided to do is we went from, well, what I showed you last time, the hybrid thing, is we went from high to low. So we had a loop that took us on that voyage, right? All right, so let's start with that, dude. So we'll have a for int I is equal to low. I said low, high to low. It's low to high, right? I is less than or equal to high in this case, that's with the understanding that we're passing our high in as the actual last position, not the one greater than the last position. So whatever we write here needs to be compatible with our Boolean expression here. If I had not put the -1 here, I would just say less than right here. All right, so they ultimately say the same thing. All right, so now we'll say I plus plus. So this loop is going to take I on a voyage between across all the legal positions in our array. Okay, and what we decided we were going to do, so for instance, we would start here at low. Now we could put a slight optimization in here and actually start at low +1, because we know we're not going to be doing any swapping here starting at low. Okay, so if we want to say, hey, we're going to be a little bit intelligent here, so we'll start at low +1. The advantage of that is we don't need to worry about the initial thing of saying, is this guy in a legal position the very first time. All right, so we'll start at low +1. So we're currently sitting, let me give myself a, let's see, how do we, do I have a fireball? Do I have, no. What other emojis might there be?
There's just like a fire emoji.
Fire?
Yeah.
Oh, that's fire. Ah! Ha! That's I. And then what should our pivot be?
Water.
Water? That's kind of dumb, but okay. Oh, you want a droplet or a splat? Oh, shower head. Nailed it. Is that a shower head? Yeah, I think so. And what should the follower be? Is there like a, it's like, oh. Skull. Yeah. Oh, so good. Oh, my new favorite thing. I have to put like a Dungeons and Dragons, like a little key down here. Skull equals follower. Fire is I. Shower head is the pivot. So good. Okay, so somebody has to remember what those are, because very quickly the things are going to go loopy in my head. All right, so we're going to have our current position of I. That's this guy right here. We're going to need a variable called follower that's going to help that guy go back, and that comes from insertion sort, right? That's our that insertion sort algorithm that we've kind of built inside of there. So let's just go ahead and give ourselves int follower out here, just so we have that variable accessible to us. We don't have to give it a starting value, although we certainly could. But each time through this loop, what actually is going to happen is follower is going to get initialized to the same place as I is. That's where he's, because I is not going to move backwards, right? As we do our swaps, follower is going to do the following, all right, to do our swaps. Okay. So what we're trying to do is we're positioning these things. Did I screw up? Oh, that was out in the hall. Okay. So one advantage of what we're doing here is our data ends up getting more ordered as we go along. So we're going to actually have fewer swaps later. All right. So what we could say is that any way you cut it, we're going to have the same number of swaps, right? We're just doing more of them early on in the application, which actually has an advantage, because now we're going to have a smaller amount of time in our later recursive calls when memory maybe starts becoming a questionable type thing. Again, this is all maybe, let's just say, not that important in the big scheme of things. But, whatever. It lets us practice insertion and sort, so we killed two birds with one stone. That's the saying, right? My neighbor uses a different saying. I think he says something like "stone two birds with." Yeah, he's kind of a potty. Yeah,
The one that's kind of loopy, right?
yeah, yeah. He's actually one of my best friends from church. But yeah, the guy's got. He's interesting. That's what it comes down to. This is actually kind of funny. So every time he sees me, this is just his thing. He flicks me off. All right, and it's just like our thing, I guess, right? So this one day, this was recently, he was doing snow removal. He's got a little tractor. He's out in his front yard doing snow removal. He's heading the other direction. I back out of my driveway, and because my driveway is actually on a separate street where I'm on the corner, so we're like this. So I back out my driveway, and I'm coming this way, and he's heading away from me. Right. So as I'm coming up on him, I'm doing the thing that we usually do, and he doesn't even know it's me. Okay. He turns, and he's already got it up. Okay. This could have been anybody. He was ready. He was ready. He told me later on. I talked to him that night. He said he just sensed me, and I believed him. Because I did impress upon me at that exact moment that he definitely had it up seconds before he saw me. So yeah, it was impressive. All right, so we're currently on I. We're going to take this guy and we're going to find out, does he need to come before the guy before us, right? All right, so does the current bucket I come before the guy before him? We still need to ask the question to make sure that the guy before him is a legal position, right? Because eventually the follower is going to get up to the dude before us. All right, so we need to first ask, is my position at least one greater than low? That's really the question we need to ask. As long as I'm at least one greater than low, which means at least as long as I'm greater than low, I'm allowed to ask the question, should I swap with the dude before me? Okay, and follower is the guy we're going to use for the swapping. All right, so we're going to ask the question, if follower is greater than low, then we can ask the next question. All right, so we set follower. Now, this inner loop here we're going to keep swapping until we can't swap anymore, right? So this is actually going to be inside of a while loop. So we're going to do while something is true, then we're going to keep swapping. So the first thing that needs to be true is follower has to be greater than low. Otherwise, we shouldn't even ask the question. And remember, with ands in any modern language, it won't check the second half if the first half is false. It's a waste of time. All right, so we know if we're getting to the second conditional, that the second Boolean expression, that we're allowed to at least legally access those positions. Okay, so if follower is greater than low, and where are we at here? This dot data at bucket follower. See, if I had the emoji thing, I could put a little skull in there. That'd be way smaller than the word follower. Okay, so if this dot data at bucket follower is less than, and you could say less than or equal to, or if you want, but why waste your time swapping if they're the same, right? So if this dot data at bucket follower is less than this dot data at bucket follower minus 1, if we should swap. And let's leave it at that for now, because we need to throw that logic. Oh, actually, we know. Remember, we ran into the thing where we don't need to worry if the pivot is in the one place, right? All right, good. So if follower is greater than low, and this dot data at bucket follower is less than this dot data at follower minus 1, what's this guy complaining about? Oh, those are strings. That's right. That's right. So, so we need to compare strings. Okay. So the less than sign doesn't work for strings. Okay, we're not able to say should this string come before this string using less than. So what we use compare to passing it the other string, and this guy's going to actually return an int. Okay, it's going to return an int equal to 0 if they're the same. Okay, it's going to return an int less than 0 if the guy before should come before the guy you passed in. So if I say, if this guy returns less than 0, so if this value should come before this value, the result will be a number less than 0. I think that's correct. Yeah. Otherwise, it would be greater than 0. Typical implementations will be -1, 0, and 1, but historically, you cannot trust that. Historically, it's 0 is the same, less than 0. The first guy comes first, greater than 0, the second guy comes first. Okay? And I think had I shown you that before?
I think the compare to might have been in her book.
Okay. It just might have?
I'm pretty sure it was.
Okay. So I didn't completely screw you over, right? That was pretty loopy when I gave you the assignment.
Yeah.
All right. So we had a fighting chance with the compare to, is what you're saying?
Yeah.
Okay.
To be honest, I used ints instead of strings just because you said, like, it was in the book, and they only ever talked about ints in the book. So I was just like, I'm just doing ints.
Oh, I got you. So, well, isn't our A list a list of strings?
Yeah, I just changed it.
So you cheated.
Yeah.
I get it. Makes sense. I guess given the circumstances, I'll just allow it because, frankly, I don't even remember writing the assignment, to be very honest. So we're practicing the compare to now. I think we could all, I just wrote the thing for comparing ints. So you've seen that version. Now you see the compare to. You cheated. That's just sad.
You said as it was in the book.
Did I?
Yeah. Yeah. I think you said implementation as it in the book. They used ints. I was like, I'm using ints.
Fair enough. All right. So if we're allowed to check the dude before us and I should do a swap, then let's do a swap. All right. And, it's probably most of our modern languages will let us do this. Let me do it real quick, and then I'm going to kind of tell you that's sort of a bad idea. So I'm going to create a string on the fly here, and maybe we call this guy, do I have a temp in here already? That was from our reverse, right? So we'll just call this temp for this is going to be like the dude we use as our staging area for our swap. Because when you do a swap between these two, we kind of need to take, this guy, put him here, this guy, put him here, then this guy, put him here. Right? You need to kind of have a temporary staging area for that. So we'll set string temp equal to this dot data at bucket follower, or you can do follower -1. It doesn't matter which one you stage there, but which one you stage here is going to dictate your next step. All right. So now we'll replace this dot data at bucket follower. Now that we've preserved him, we'll replace him with this dot data at bucket follower -1. Then we'll say this dot data at bucket follower -1 is equal to temp. All right, so that does our swap, right? And then the follower follows. That's why we made it a skull, right? So follower -. Okay, or minus equals 1. What do you pick your poison? Remind me. Follower --- versus --- follower. What's the difference? In this case, there wouldn't be a difference, but under the hood, functionally, those things are working differently. What is the difference between the --- coming before, the --- coming after, or the ++ coming before, and the ++ coming after? Oh, go ahead. I'm pretty sure she knows the answer. Go ahead.
It's in the for loop, it'll affect whether it's implemented before or after.
Okay, so when the --- comes before the word, that increment occurs first, and then that portion of the code. So this guy right here, if we were to use that in an expression, minus minus follower would boil down to the value that is one smaller than the follower, right? Because the decrement happens right away, and then we get the new value. When the minus minus comes afterwards, what I have highlighted there would boil down to the current value of follower, and then the decrement happens. Okay, so it does have it potentially, depending on how you use it, could have a difference. Now, my typical recommendation is nobody's impressed by you stringing all this crap together, so most of it really shouldn't matter which of those two you use, because you should be using them on independent lines. But every now and then, as long as you know what those guys do, it might be beneficial to be able to do that in line in some expression. All right, so know the difference. You can also say the compound operator minus equals 1. You know, kind of pick your poison. Take 1 away from follower and make sure follower's changed is what we're doing there. Okay, so as long as we should swap, well, this says as long as we're allowed to check and we should swap, go ahead and swap and let the follower follow. Go ahead.
Can you scroll that way a little bit?
No.
Because
Absolutely not. Here. Oh, did you get your thing fixed?
yeah.
Okay, so what we just did here, we said, should a 1 come before a 3? Yes, it should. So we went ahead and you know, this is our initial call here, so we haven't split these guys up yet. So should a 1 come before a 3? Yep, so let's go ahead and do our swap. Follower follows. Oh, yeah. All right, so follower follows. Then we loop back up. We ask the question, is the current position of follower greater than low? It's not. So we fail out of that while loop, right? Because we fail this very first part of this dude right there. Follower is not greater than low. So bail. All right. So after we've done that, what happens next? Well, we haven't changed our pivot at all, have we? So we just loop back up and keep cooking. Yeah, we got more stuff to do, right? So what happens next? We loop back up in our loop. I becomes 1 greater than it used to be. We then reset follower, right? Isn't that what happens here? I plus plus, follower is equal to the new I. Do the same thing again. Are we allowed to check? Yes. Should a 6 come before a 3? No. We fall out. I becomes 1 bigger than it used to be. Should a 2 come before a 6? Well, are we allowed to check the current value of follower? Yep, it's greater than low. Should a 2 come before a 6? Yes. Do the swap. Follower follows. Should a 2 come are we allowed to do the swap? Yes. Should a 2 come before a 3? Yes. Do the swap. Follower follows. Are we allowed to check? Yes. Should a 2 come before a 1? No. We fall out. Loop back up. I increments. Oh, what's going to happen here? We got water and fire. Oh, man. Oh, Christian worldview, Trinity. Point.
You can just start using a cross to delimit things like in a 325.
We can switch this guy to the cross. That should be the pivot, right? Was it cross?
I don't know if there is a cross emoji.
What? Hold on. That would be awesome if there was a Jesus emoji. Do a baby? Is there a baby emoji? Oh, do I want the baby face or the bottle? Kind of looks like a monkey. That might be too close to evolution. We can't. Is there really not a cross? Crucifix? Is that a word? How is there not a cross? All right, I guess we're back to the shower head. I tried, people. So that's all right. So we're here. This happens to be the pivot, right? Okay. Not all that important to us, but we do need to remember where the pivot ultimately is going to be. Okay, so that shower head's gonna have to follow here, right? So our pivot's gonna move along with the follower. So that's where this extra line of logic is gonna come in that we're gonna discover here in a moment. Okay, so we asked the question: are we allowed to compare? Yes. Should a 7 move? I want to cheat for a second. I want to do that. Let's pretend it was a 5 all along. All right. Because I want it to actually move. That way we can see the line of logic. All right. So are we allowed to check? Yes. Should a 5 come before a 6? Yes, it should. So we're going to do our normal swap. Follower follows. Okay. But we need to make sure that this guy also we keep track that pivot just changed. Does that make sense? So we need to ask, when we're doing the swap, if we're swapping pivot, that is, if skull, what was the guy called? Follower? If follower, see, I told you I'm going to get loopy on this. All right, so if follower is equal to pivot, we need to also decrement pivot. Make sense? So if we're supposed to follow here, we can go ahead and do our swap, no harm, no foul. But before we decrement follower, we're going to say, now you actually could, this is one of those examples where you could use the follower minus thing. So you could actually do, let me just show you an example of it since it just happened to present itself. So if follower minus is equal to pivot, then you would say pivot minus. So you would actually look at this and say, that looks funky, right? But remember, this guy right here will actually provide for me right now the value, the current value of follower, because the minus is afterwards. So I'm saying, is the current value of follower the same as pivot? If yes, decrement pivot as well. Regardless, follower is going to become one smaller than it was before, but only after I've already done the comparison. Does that make sense? And do you see kind of what I mean, how this can be confusing when you look at it? Right, so I would typically write it like this. If follower is equal to pivot, have pivot follow follower. Any way you cut it, follower is going to become one smaller than it was. Make sense? So what I have written right now is functionally equivalent to what I had there before. And nobody's impressed that you wrote the thing that was there before. Okay? People used to do that stuff years ago, and it's kind of been left over from that. I think it's kind of, I don't know, in the programming world maybe has gotten like a cool kid vibe or something, or following. It's like, if you write complex code, some people view it as job security. If you write code that nobody else can read, or people don't know what it's doing. But it's, trust me, nobody's impressed. Okay. All right, so this guy will conditionally make sure that our pivot moves. And the whole reason that we need to make sure we keep track of pivot is because our next call to our quicksort is going to be relative to pivot, right? It's going to be everything to the left of pivot, and it's going to be everything to the right of pivot, because ultimately pivot's going to be where we want it to be. Make sense? All right. So since we're moving pivot now, we need to make sure that happens. So pivot moved along with that guy in this particular case. Then we say, are we allowed to swap again? Yes, we are. Should we swap again? No. So we're done. Increment I, reset skull, reset follower. Oh, why can't I just call it skull? That would be bad programming practice. Yeah, you just have these variables, fire and skull and the shower head. Shower head's going to creep people out. Trust me, that will happen. All right. So, what was I talking about? Okay, yeah. So we pivot has moved currently, so that's fine. So are we allowed? Now we've reset. Are we allowed to swap? Yes. Should 4 and 6 swap? Yes, they should. So let's do our swap. 4 and 6. Go ahead and follow. Now, one thing we could have. No, that actually won't work. This is fine. So we'll go ahead and follow. Are we allowed to swap? Yes. Should we swap? Yes. Swap the 4 and the 5. All right. Are we allowed to swap? Yes. Should we swap? No. Increment I. Reset follower. Are we allowed? Yes, should, no. Are we allowed? Yes. Swap the 3 and the 7. Follow. Swap the 3 and the 6. Follow. Swap the 3 and the 5. Follow. Swap the 3 and the 4. Follow. We're not going to swap the 3 and the 3 because 3 is not less than 3. All right, so we're done. Increment I, reset follower. Are we allowed to swap? Yes. Should we swap? No. Now we're done with our for loop. Now something we should notice here is our data is currently sorted. Is it guaranteed to be sorted using this hybrid approach? Is there any circumstance when it wouldn't be sorted after our first pass? What we've effectively done here is we've performed an insertion sort across the entire data set. Did we need to do that? I mean, we could have done that. We did do that, right? I mean, we just wrote insertion sort, and we just happened to keep track of a pivot along the way. Well, when should we have used that pivot? When could we have used that pivot? So remember, the whole point of Quicksort is make sure that everything that is greater than our pivot gets to its left, and everything that's, less than our pivot gets to its left, everything that's greater than our pivot gets to its right. Okay? We can use a hybrid insertion sort to bubble it that direction. But what we did is we effectively just completed insertion sort. So we really did more work than we needed to do. We ultimately got the stuff sorted. But at the end of the day, could we call this a Quicksort? Or is this an insertion sort that we keep track of pivot? So we did more work than we really had to do here. How would we have modified this to turn it into our hybrid Quicksort as opposed to this? or really any kind of quicksort. I'm really shooting for the hybrid quicksort. When we first started, we had our pivot here, and let's just assume our pivot's right here. We don't know for a fact, right now we do, but when we first started this data, we don't know for a fact that everything to the left is smaller than it, right? We just know that it's not the pivot. We don't know that everything to the right is larger than it. We just know that it's not the pivot. We don't know if our pivot is in its final resting place, right? We just know that it's the pivot. So if we break those three problems apart and we say, what will it take to ultimately position our pivot at its final resting place? Remember last time we mentioned that it's often a good idea to choose the final bucket for your pivot. Yeah, remember that guy? So if we use that just as a thought for a second, if we had chosen our last bucket as the pivot and we said, okay, we're going to bubble this guy towards the front as far as he can go. That's effectively an insertion sort move, right? Okay. Which I always found funny because doesn't that sound like a bubble sort move? But it's not. That's not how bubble sort works. As I think about it, as bubbling towards the top, right? It's an insertion sort move. Okay? But if I start at the end, and I just go ahead and I bubble that pivot as close to the front of the list as I can, what do I know at that point in time? What facts could you tell me about that? I have taken pivot as close to the front of the list as I possibly can.
It's in its final location.
Let me just make sure that's true. I think you're right, but let me just, that wasn't the first thing I was looking for, but well, so let's follow the logic and see if we stumbled upon it. We know that everything to the right of it is greater than or equal to it, using our less than logic, right? So we know everything to the right of it is greater than or equal to it. Now, what about the stuff to the left of it? Do we know for a fact that everything to the left of it is greater, or is smaller than it? We don't know for a fact. Okay. We know that the guy just to the left, okay, we hit a wall, right?
Because it's not checking once.
We haven't gotten all the way to the front. Yep. So we don't know for a fact he's in his final place. Okay. But we know that he's very well. I don't know that we can honestly say closer because you may not have actually moved him at all. But we know that he is likely closer to his final resting place than he was before. Okay, so we've moved us in the right direction, okay, using an insertion sort bubble. All right, so now we got him here. So now the only stuff we need to worry about is the things before him. All right, and what we're interested in is, are any of these things bigger than our pivot? Should any of these things be on the other side of the pivot? Are they positioned incorrectly right now, right? So we would start with we know the guy right before him is currently in the correct place, right? We know the guy directly to the left of our pivot in this model should be to the left of the pivot. So really we care about the stuff before him, all right? So however many things there are, might be one thing, might be 0 things, might be 20 things. Okay? So we actually care about the position of pivot minus 2 from low to that guy. All right? And we want to take any of those things that should be on the other side of pivot and put them on the other side of pivot. That makes sense? So as we're going through that list, and each guy we find, we say, okay, well, should this guy be on the other side of pivot? If yes, let's assume the answer is yes. What do? So we're taking him out. We need him to go on the other side of pivot. We don't care where on the other side of pivot. Okay? I mean, we just wrote insertion sort, so we stumbled upon this thing that, hey, everything's sorted. I'm kind of done. Okay, but this wasn't a quick sort, right? Like, oh, I had minimal recursive calls. Is it none, right? We don't care whether the stuff is sorted on either side. We just care that the stuff is on the correct side. So if I find a dude before the pivot, after I position my pivot, kind of in the insertion sort way of kind of getting it as close, kind of an approximation of final location. And I say, okay, well, I'm going to start at low and go all the way up to pivot -2, including pivot -2. Because I know pivot -1 is less than pivot. Don't need to check that guy. Okay, so I'm going to start at low. And if I find any of those dudes that really are on the wrong side of pivot, I can take them out, move everything else over, drop him in the old location of pivot. Right? And do that until I've done that for all those pieces. Does that make sense? All right. At that point, I know that my pivot is in the final location. At that point, I know everything to the left of pivot is less than pivot. Less than or equal to, I think is the logic we've been using, right? So I know that everything is to the left is less than or equal to pivot. I know everything to the right is greater than pivot. Okay. So right now we are compatible with Quicksort. So right now I know pivot is in the final resting place, so I know I need to call Quicksort on everything to the left. So that is low to pivot -1 and pivot +1 to high. That make sense? All right, so let's go back and modify this a little bit. We're still doing the insertion sort move. Okay, we're just not doing it across everything. Okay, we care about our pivot. And it's very important that we pick that last bucket for the pivot. Okay? Otherwise, we don't have that initial assurance that everything to the right is greater. That makes sense? Now do we see why it's important we pick that last bucket? We don't have to. But by picking the last bucket, so I think that you had read about, or at least I referenced it from the Wikipedia page, right? So the Wikipedia page kind of alludes to this optimization. Okay, that initial bubble move, which isn't part of the traditional algorithm, because the traditional algorithm lets you haphazardly pick a pivot. Doesn't matter what pivot you pick. Okay, but then you kind of need to deal with both sides similarly to what we just did, right? And then your swaps kind of, you can use that algorithm we just talked about for your swaps, or you could use a different one. But anyway you cut it, you end up having stuff on the right being bigger, stuff on the left being less than or equal to, and now we can move on with our recursive calls. So our first move here is we're going to set pivot equal to high. That's the far right bucket. All right, we're going to still have our follower. And what we're going to do is we don't need this for loop right here. All we're interested in is so we're going to say follower is going to start to be equal to pivot. Do we need follower in this case? We don't need follower in this case because pivot is allowed to move, because ultimately we need to keep track of the final location of pivot. So we're going to dump our skull, which is upsetting. But not that upsetting. All right. Shower head's gone. Skull moved into its place. So pivot equals the far right bucket. Let's get rid of this. Actually, let me just steal our initial while loop here in the middle. We'll just modify that guy. Dump this stuff. So the only move we're doing right now, we're not doing this across everything. We're doing that bubble move, that internal while loop for pivot only. All right. So while pivot is greater than low, and this dot data at bucket pivot compared to this dot data at bucket pivot minus 1 is less than 0, then we'll do our swap. Pivot, 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 pivot. We actually won't need that, but we will need the pivot minus. That makes sense? So after that while loop, now understand what we had written before was insertion sort with this random thing called pivot sitting in there, right? That we just kind of said, oh, we're going to move this guy around. But that was insertion sort. Check your book. It's the same algorithm. All right? So now we've taken that insertion sort logic and applied it only to pivot with the expectation that pivot started on the far right. Okay? So when we are here, we know that everything to the right of pivot is larger than it. That's what we know for a fact right now. We can suspect that pivot should be close to its final location. But we really know, we also know, we know that the element directly to the left of pivot is less than or equal to it. We also know that. Otherwise, we would have hit our swap. You know, we would have done the swap. Now, there is one possibility here, one optimization we can do here. It is possible that pivot is currently at low. And if pivot is currently at low, that means that we've actually put pivot in its final location, correct? Because we didn't stop because we were done swapping. We stopped because we weren't allowed to check anymore. That makes sense? So we can now ask, so we can say, or pivot is at its final location if it is equal to low. So if pivot is equal to low, we don't need to do that move of handling the crap to the left of pivot. Now the reality is we could, we're going to see the logic for that is we wouldn't actually deal with it anyways because we'd have a for loop that tried to do everything from bucket low to bucket pivot minus 2 inclusive or less than pivot minus 1. And that loop would just, it's a pre-check loop, so that loop would go through 0 times, right? But if we say pivot is equal to low here, if we ask that question, we know that we actually only have one recursive call to make, correct? We know that pivot's in its final location, and I only need to handle the other side, the right side in this case. And I actually only need to do that if the current location of pivot is also not equal to high. Because remember, we might be down to that one list, right? So if pivot is equal to low and pivot is not equal to, or we could say pivot is less than high. What does that say? That says that we don't have a left-hand side. And at the very least, we have a right-hand side of size 1. We could insert some optimization here and say, well, if it's size 1, let's not waste our time. We could do that and save ourselves a recursive call. So because we talked last time that the problem with recursive calls is memory, correct? So we could cost ourselves an extra little question here, and we can say if pivot is less than high minus 1. Okay? If that's the case, then we know that at the very least there's 2 elements on the right-hand side. That makes sense? Now, understand that what we're doing is we're trying to handle a special case right here. Now, we're going to find out whether the special case is helpful here in a moment. So we're going to go ahead and write it since we're letting this code grow organically, but we might find that the final loop that we write ends up naturally handling this. All right, but let's go ahead and write it. So if pivot is equal to low, and which means we have no left-hand side, and pivot is also less than high minus 1, which means we have at least a 2 list on the right-hand side, then we'll go ahead and call Quicksort on the right-hand side. So we'll say this dot Qsort, where low is going to be pivot plus 1, and high will be high. And that's the single recursive call that time around, because we know the left-hand side is where we're cooked. Else. In this else, we know that pivot is not at the beginning of this thing. Let's see, we don't necessarily know that pivot's not at the beginning of this. Since we did these two things together, these are an and, we could potentially be in this else when pivot is equal to low, but high is not the 1 list. So this logic needs to be represented, but maybe not there. So I think what's going to be the safer call for us then is for us to go ahead and write the for loop to handle the stuff before pivot, knowing that that stuff might be nothing, and the for loop should handle that. So, we're going to go through all the values. We're going to say for int I is equal to 0, I is less than pivot minus 1. We can say less than or equal to pivot minus 2, or just less than pivot minus 1. I plus plus. So this will take us on a voyage between all the values through all the values left of pivot currently. I should be equal to low. You're right. So we'll start at the beginning of our list, whatever portion of the array we're in. It won't necessarily be 0. She's right. I was testing you. All right. And we're going to keep going as long as we are left of the guy left of pivot. And we'll add 1 to I each time. And what we're trying to do here is we're seeing, do any of these guys need to be tossed onto the right-hand side of pivot? If they do, what we'll do is we'll preserve it. We'll shift everything down, giving ourselves an empty bucket. Then we'll put that guy in the empty bucket. All right. So if this dot data at bucket I is greater than this dot data at bucket pivot. If that's a true statement, then I need to preserve this dot data at bucket I, because that means that the current bucket I'm looking at actually needs to go on the right-hand side. Make sense? So I'll say string temp, although this is the compare to thing, right? So we need to, because these are not integers. So compare to this guy greater than 0 this time. So if this dude should come after this dude, compare to will return a number larger than 0. And if that's the case, we want to preserve this value, this dot data at bucket I. Then we want to shift everything left from bucket I to pivot including pivot. We want to move them one left to where they currently are. All right. So we're going to have another for loop. So j, let's say, is equal to I. J is less than or equal to pivot j plus plus. So this is going to handle all our indices from right now all the way up to pivot, and we want each of these guys to be one before. We want each of these guys to shift left one, knowing that we're allowed to destroy the guy before me. All right, so we'll say this dot data at bucket. Let's see, we actually want to say I plus. This should be I plus 1. We're going to start one ahead and shift it left. So we're going to say this dot data at bucket j. I'm sorry, bucket. Actually, I guess it doesn't matter if we say I plus 1 there or just I. We need to shift everything left. So I can say this dot data at bucket j is equal to this dot data at bucket j minus 1. And with that in mind, we do want to go up to pivot, including pivot. That's good. So this dot bucket at j is going to be equal to this dot data at bucket j minus 1, or j plus 1, I'm sorry. The guy to the right. So I'm taking the guy to the right and moving him here. I actually copying him here. So for a second, he's going to live in both places until I copy this guy here. Okay? So ultimately, I'm going to keep moving things left, 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 left until I finally move pivot to the left, giving me an open hole here that I can then put temp into. So after I've shifted everything left, I can then say this dot data at bucket pivot, because that's actually where the hole is, right? I have not modified pivot right now. So pivot actually points to the hole currently, where the actual pivot is 1 to the left. So this dot data at bucket pivot is equal to temp. And then pivot minus minus. That makes sense? So this will go through everything to the left of pivot and shift anything that actually needs to be to the right of pivot to the right. After I've done this, my last two things, I know we're out of time here, so we are out of time, right? Starts at 11:20. So I'll just put a little comment in here for us to just finish it last time. We have our 2 recursive calls, and let's just say potentially 2 recursive calls. So let me just give you a thing out of the book to look at. Have you started the linked list section yet? Okay, but we finished the searching, sorting stuff, right? Okay, so let me bring up the book real quick, 300. So we're starting chapter 2. Read 2.1 and 2.2 to introduce you to the singly linked list, and then we'll finish up this guy next time and see it work, and then I'll start my introduction to linked lists. Sound good? All right, I will see everybody on Tuesday. Have a good weekend.